Hi everybody! Now let me introduce you a new application, EasyRebalancing. First, I will walk you through some background about this application. In 2013, the city of Chicago launched Divvy, a new bike share system designed to connect people to transit and to make short trips across town easy. While the system is experiencing growth in usage, it also faces a big problem. The unbalanced bike flows result in empty or full stations frequently, making the bike share unreliable to use. This largely contributes to the loss of potential customers. Currently, DV staffs drive vans to reallocate bikes based on the real-time availability, which usually lag behind the need due to the time of driving across the city, especially during rush hours. Furthermore, research has shown that rebalancing is the single largest operating expense for bike share, which is up to $1,944 per bike annually. EasyRebalancing is designed to solve this problem by improving the effectiveness of rebalancing operations, minimizing the imbalance of bikes, and reducing the operations cost. Using this application, the staffs can not only check the real-time availability, but also see predicted imbalance of bikes in the next hour, so that they can plan for rebalancing in advance to make it more effective. The main interface of the application consists of two components, a top bar for user inputs and an interactive map to visualize conditions for each station. At the top bar, the user can specify the type of map they would like to see, such as real-time availability of bikes, historical hot start stations and end stations during current time of day, and predicted imbalance for each station. By checking these remaps, the user can get a sense of where the bike stations that are most in need of rebalancing are located. The user could use zoom in, zoom out, and fly to current position buttons to see the condition of nearest bike stations. The routing function provides optimized route of rebalancing based on both the severity of predicted imbalance and current traffic condition. The top right search bar allows users to fly to a specific location on the map. The user could also click on each bike station to check out the basic info from the pop-out and detailed statistics in the sidebar, such as predicted rebalancing need for the next hour. These statistics could help the DV staffs make decisions about how many bikes they want to refill or remove for a specific station.
So how does EasyRebalancing work behind the interface? Well, this app is supported by two similar models that predict the hourly departure and arrivals of each station, with which next hour bike and dock availability can be calculated. In this demo, we will only go into details about hourly departure model. It was built on 147 stations near downtown Chicago for the second week of June in 2017. Because there are greater rebalancing demand due to the prominent commuting pattern in warm days, as shown in the two graphics here. Our candidate predictors include variables that are theoretically related to bike travel demand and historical departures of stations and their neighbors. Because demands are usually concentrated in certain time of day and locations, which will repeat week by week. Based on this data, we built a linear regression model. Candidate predictors are selected based on their explanatory power. To test if our model is generalizable enough, we train the model for 1 week, predict for the following week, and compare the results. The final model consists of 12 significant variables, among which historical departure is the most important predictors, followed by departure time, neighboring station departures, real station ridership, and employment density. The model explains 70% of the variations in hourly departure, suggesting strong explanatory power. But as shown in the scatter plot, our model underpredicts stations with extremely high departures. To test the generalizability of our model, we did 3 validations, all of which suggest that our model is generalizable. First, the 100-fold cross-validation shows that the average error concentrates around 1.55, indicating consistent predictive power across different observations. There is also no significant temporal autocorrelations, since errors are randomly distributed across the day. The results of weekdays and weekends are comparable. In both cases, about 75% of the variance can be predicted, and the average error for each station is about 1.5. Lastly, there is no spatial autocorrelation among errors, as they are randomly distributed, indicating consistent predictive power across space. The statistical test for spatial autocorrelation suggests the same conclusion as well. With easy rebalancing, we can help you identify rebalancing needs in your system, boost your rebalancing efficiency, and save your money. Thank you for listening. We welcome any comments and questions.